Hello, everyone. Welcome to today's SciML seminar. We've got Xietao presenting his work on active matter being predicted with graph neural networks. Without anything further, I'll hand it over to you and you can give us your presentation. Thank you.
Thank you, Miranda, for inviting me, and it's my pleasure to be here. I will be talking about how can we use graph neural networks to, in a way, predict emergent behaviors in active matter models. So first of all, I wanted to talk a bit about the motivation behind the project. The motivation was to how can we accelerate agent-based simulations, and there are two bottlenecks of why agent-based simulations are slow. So, and by agent-based simulation, I mean you consider each agent individually rather than the whole ensemble together. So there are two bottlenecks why this is slow. So one of them is that a lot of times the simulation requires very small time steps. So one example of this could be what we'll use is molecular dynamics, where the time steps is of the order of 10 to the minus 15. The simulation needs to run until the order of seconds. So that's 10 to the 15 times that you have to take. So we wanted to use machine learning in order to speed this up. So this data-driven model needs to, in a way, skips time steps, or integration time steps, or in a way take larger time steps. So we call this that the machine learning model should be able to perform temporal coarsening, which what we call it. And the other bottleneck is in the scaling of the on the number of particles or agents. So if we call that n, and we go back to the molecular dynamics example, we see that the time complexity of the simulation scales at, depending on what potential you use, of n cube or even n fourth, or sometimes even worse, depending on how complex you want it to be. So if we were to train a machine learning model on this, in a way, we're kind of forced to use smaller systems, because the bigger system is completely intractable the moment we scale it up a bit. However, this presents now with another question, which is that we might run into a scenario that is the model manages to learn well what happens on the small scale system, but doesn't recreate what happens on the larger scale system. And so if we take, for example, this block of birds, we would like to so each agent here is a bird. We can imagine a scenario that we can replicate what happens on one bird, but the moment we put it together, it completely fails. So there's that. And the way we're gonna, in a way, test this is if we're gonna use active matter systems. So this, and by active matter, it's basically active matter is anything that's taking energy from the environment and use it to propel themselves without external forces or anything like that. So one example of this, there's many examples you can draw from the literature. One of them could be actual people. So we metabolize energy and we walk. And then again, the birds, or stuff like bacteria in biology. We will use active matter because I mean, the field is not very old, but we know that there's a lot of emergent behavior that comes up the moment we scale up. Yeah, but for now, we'll leave it like that. We'll talk a bit more about the machine learning background for agents. So we know from the literature that we have models that can perform like this temporal coarsening we mentioned. So basically, this is if you were to imagine an agent system. So instead of integrating the red path, the temporal coarsening model will just skip the entire integration step and just it's the green line over here. It just skips the integration step. We know from the literature this is possible. There's many models that have done it before for like people or fluids or like other stuff. However, the other part of the question is whether that does the scale like generalize beyond the training distribution is not well known. So that's where we're gonna focus here. And that's so if we were to like delve into the literature, most of the data sets they use, and the test environments are very similar. So they're basically trained on the same the training distribution is like very similar to the test distribution. So it's basically just focused on the temporal coarsening, but not so much on the scaling part of the problem. So we're gonna use active matter here to like prove generalization properties of the learned models in terms of first of all increasing number of agents. Secondly, if we were to do very long rollouts, and lastly, we'll investigate whether it can like generalize in novel geometries. Okay. And now for the actual methods. Surprisingly, the main method for agents here is graph neural networks, which haven't been seen much outside of like social networks, but it has been used here apparently. So first of all, I'm not sure if everyone is very familiar with graph neural networks, so we'll go through them very quickly. So a graph neural network is a neural network that takes a graph as an input and process them so that we get some output. We'll talk about the output later on, but yeah. So first of all, the way we convert the agent system into a graph is that we have an example agent system here, and I labeled two agents by I and J. So for each agent, we look at small radius r, and if it falls within the radius, we'll connect that with an edge. And as for the nodes itself of the graph, it will be the particle itself. Therefore, the graph looks something like this. Here we have is what it is. So so the nodes will contain information about the particles. So this could be like the radius, the orientation, or the mass, or anything like that. And then the edges will also contain some vector information, which will be in here we'll use the distances. So for the architecture, it looks something like this. And as we mentioned, we'll use the relative positions as the edges, and the nodes will contain information about the particle. So basically, the first step here is to pass this to an encoder to lift them to a higher dimensional space. But that's the standard in most machine learning applications. And then after that, we have this higher dimensional graph, which will what we'll do is message passing. So basically, we'll for each node, we'll look in the neighbor in the graph theoretic sense and take a bit of information from the neighbors, and we'll repeat this a few times. That way, we can process the information through the entire graph. And lastly, for the output now, we'll take the nodes, the vector information in the nodes, and decode them into something that we can use to like move forward the simulation. Here, it makes sense because we have the current position to target the displacement. So that the future state is basically just the current state plus this displacement we just predicted. Okay, I understand this can be very confusing looking at this, so we'll look through it in a more using a diagram. So basically, we have our graph, and you can imagine that the colors could represent like a vector. For example, yeah. And then we'll do this message passing step. So basically what it does is takes information from the neural nodes and like in a way convolutes them, similar to what a convolutional neural network would do. And then we repeat the step many times, and you can imagine that the information will reach farther than just looking at the neighbors after many repetitions. At the end, we'll get the same graph but with different information on the nodes. What we can do then is take a neural network and decode this into the velocities we want, or like displacements. And as for the edges, we just discard them. We don't need them anymore. And with these are now displacements, all we have to do is add them back to the original positions by summing them. And then we repeat this process. So we convert this back to the graph and repeat this until we simulate whatever we want to simulate. Okay, another analogy you can make out of this is that the graph neural networks you might have heard that are in a way generalizations of the transformer model, except transformers are assumed to be a dense graph, whereas the graph neural network we have flexibility on how we choose a graph. Okay. With that in place, training the graph neural network to simulate, it's straightforward from here. So basically, we take a random set of initial positions and then simulate them using a standard method to obtain a future state, t plus delta t. Here we make sure to choose delta t to be quite large than what the solver usually needs in order to achieve this temporal coarsening. Yeah, so basically we just get has many pairs of this t and t plus delta t, and yeah, all we have to do now is pass y into a graph, obtain a prediction of the displacement, which will just use like gradient methods and minimize the mean square error to do that. Okay. So now back to active matter. Again, these are these particles. The particles are we're gonna be studying here. It's gonna be simpler than this. It will not be actual people. That's unfortunately it's too difficult right now. So we'll look for now at what we call the active Brownian particle model. So these are basically just particles that have a preferred orientation and they just move forward. And yeah, that's it. So it looks something like that. So each particle has is orientation, and we just move forward. And if they hit another particle, they will try to repel themselves from each other. But that's about it. We don't have anything fancier than that. So this term over here is the proportion term, and this term is the repulsion term. Okay. Although this may not look very interesting, the thing is, the moment you scale this model up, you will see as what we call emergent behavior in active matter. And so, okay, so here I have a bat of, what's it, 2,000 particles. And the density is about the same, except now, if you simulate them, you will see that there's a few clusters over here that may start forming. Even though we don't have attractive interactions here. So with just repulsions, and now, of course, we have the activity, particles naturally like cluster. Even and more importantly, this phenomenon only happens whenever we like scale the model up. So the hope here is that we're gonna train our graph neural network. Yeah. Yeah, periodic domain. Yeah, so the idea here will be to use the graph neural network to like train on data that looks like this. And when we can scale this up, can then use the graph neural network to like infer on a larger path, like that looks like this, and see if we can recover the clustering. Okay, so we'll do that. We'll do that now. See if it works. So we do that. So we can generate the training data, train the model, and then now this large path is completely unseen to the model. And for reference, the training data has at most like 70 particles, 70. And here again, we have like a few thousand particles. So if we run the simulation, speed it up. But yeah, you'll see that the trajectories do diverge very, very quickly, but that's to be expected with this like very chaotic simulation. We can see that we get back the clustering back, which is good. That's qualitatively, this looks good to me. And quantitatively, well, what we can measure here is how big these clusters become and how many particles are what we call cluster in a way. So, and that's what we do. So here on the top, I have the number of particles that are in a cluster, in any cluster. On the bottom, I have the size of the largest cluster. And again, the training data is like 70. And so anything over here is not seen to the model. And from here, we can see that although the clusters get a bit larger because of the repulsive force, it's a bit understated. But we can see that the models manages to like, between 500 and 1,000, the model starts to predict this. The clustering becomes slower, and that's in a way predicted that the cluster gets more stable over time. Whereas when we have fewer particles, this very fast clustering indicates usually that the clusters are very unstable. Other than that, we'll move on to the next poster child, I guess, of active matter, which is the Vicsek model. So the top equation remains the same, except now the orientation of the particles can change. So what we do here is, so this term over here is what we call an alignment interaction. So whenever two particles are close, they will try to align themselves with each other. So if they are pointing different direction, whenever they're close, they will try to point in the same direction. We also have a small rotation, but that's fine. Okay, so now again, we'll do the same procedure. We'll train on like 70 particles or so, and we'll infer on this path of about 2,000 particles. Here, what we'll see is that the particles, because we don't have noise in the model, all the particles at long times should synchronize. So if we do that, okay, it looks like now the particles are synchronized, and again the trajectory is completely diverged very quickly because any small error compounds quickly, and because the dynamics are so chaotic, yeah, we cannot get a perfect match on the trajectories, and so the phase also changes a bit, but hopefully if the simulation restarts, well, I'll restart it myself. We'll see that again qualitatively it looks similar, but what we're going to try to measure here is the time that it takes to synchronize. Here, from this snapshot here, it looks like the synchronization thing is similar, and so hopefully that also stays quantitatively. So if we look at it, so here I'm plotting the alignment coefficient, so which is on the top. So the coefficient will be close to 1 if all the particles are pointing in the same direction, and will be close to 0 if they are not. And from the true simulation, we see that as we increase the number of particles, and so the density always stays the same. The time it takes to synchronize slows down. And now our machine learning model manages to replicate this slowdown, even though it has again never seen this number of particles before. So the cutoff is around there. So that's good news. We're confident now that it's learning something more than just memorizing rules at the low end behavior. Moving on, we have a few other examples. So one of them is these higher particles, except now we put a few obstacles. So we remove the alignment term and the particle just rotate. And now we have a few particles that don't move, but they are still repelling from the other particles. And what we can do with this is that if you place one of the active particles here in a lattice of obstacles. So here, let's see. Okay. So in black here, I have some obstacles that are placed in a square lattice, and I vary the separation of the lattice. And depending on this separation, the behavior can be quite different. So you can yeah. So for example, here the particle is like kind of stuck and just making these circles. And this one over here spreads a bit more. Particularly this one, it's moving. The lattice is making the particle move forward. So we can, in a way, measure how much the particle spreads. If we were to like repeat the experiment many times, in a way we can try to measure how the ensemble of active particles diffuse. So that's what we did on the plot. And the ground truth result is that we basically get 0 everywhere, except we have a peak here on number 5, which is that one. If we were to we tried repeating this using the graph-neural network, and the result is that we get the first peak, which is good. Well, the first peak, the only peak, which is good. However, we do get like a second peak later on. And this is, we'll see, is this one over here, which is, okay, so if you were to place a particle here, it should get stuck. So this is so tight, the particle should just get stuck. But if we look into it and use the graph-neural network, give you a time, yeah. You see that it's making this weird AE movements, which is weird, and obviously it's very unphysical. So you can see that the particle somehow can enter through here, but cannot escape through here or here. And because it can do that, it will enter through here and then rotate inside, and then until it exits. And so it, in a way, it does that. So which is not what should happen. So if you cannot escape from one, if you can enter through one side, you should be able to escape through the other side just fine. So if we look, and the reason behind that is that the way we set up the graph neural network is, or well, any neural network is that they're not supposed to like, well, they're not supposed. They were not made for interacting with like coordinates. So the moment you pass a coordinate through a graph neural network or any neural network, it will kill the rotation symmetry. And that's exactly what happens. So we tried whole toy system with like only 4 level obstacles and place a particle in the middle. So if the particle escapes, it should escape through here. And all we did is like rotate the system a bit, and the particle now escapes, even though it's the same system. So if we were to do this, so we do this for all angles, map this radar plot, and you can see that this escape threshold is like very irregular. So the particle, so the graph neural network predicts that the particle should escape outside the shaded area, and inside the shaded area, the particle gets trapped. And here, the red line is the threshold at this one. Yeah.
What's the difference between GNS and EGNN?
I'll explain it now. So GNS is the graph neural network we're using so far, which is not rotation invariant. So we tried to fix this by creating a graph neural network that in a way preserves these rotations. And that's the EGNN one. This one doesn't have the peak, which is good. And the way to do this is that instead of passing the coordinates to the neural network, we just don't. So we separate what we call a scalar feature. So this is the diameter and the orientation, stuff like that, from the coordinates. So the scalar features get passed through a standard graph neural network, and whereas the vector features like the positions get passed through a custom architecture, looks something like that. Yeah, basically we don't pass them through neural network, and we just don't, and just try to like integrate them without doing that. So the moment you do that, the second peak disappears. So that's good. So we found that in a way, whenever the geometry is like this very, very tight, we need to keep in mind that rotation symmetry could be causing problems. And lastly, we have one last example, and this is, so this is, as it is. So we have the first equation says the same, it's the active particles. And the second equation is in a way like a static torque. So when particles collide, they will rotate a bit. And now we're gonna place the particles in the same path, but we're gonna place like this chevron-shaped obstacle in the middle. Okay, and what this should do is that when the particle enters here, the torque is going to rotate the particle so that the particle points towards the apex. Well, just a bit, just enough so that it gets stuck in the chevron. So if we were to simulate this, the particles will just go in and get stuck. And the other particles don't have a space to go, so they will just float around. So now the parameter here that we're looking for, so qualitatively, again, that looks fine. But quantitatively, the parameter we're looking here is how many particles are in the chevron. And depending on the opening of the chevron itself. So if we do that, we got something like this. So blue is the ground truth. And we try three graph neural networks depending on the data set size. So we can see that for this one, because the problem is a bit harder, we need, in a way, more data to do that. And we expect the gap to like close the moment we have infinite data, but we haven't run the compute for that. But yeah, you can see that the usual case of like few thousand points that we usually have, it's not enough, and that causes like the particles to like have some bias in the angular prediction. It's like a small bias that makes the particles continuously rotate, that eventually causes the particle to like the exit the chevron. So that's why we don't have anything here. And this bias gets reduced whenever we scale the model up until we have something like looks reasonable, I guess. Okay. Lastly, we'll talk a bit about the metrics that are actually used in the literature, in the machine learning literature, not in the active matter, of course. So first of all, we see, if we look at the time, that the speed up is very large. It's like 20x. Sometimes we even get more depending on how the experiment is set up, which is good. And I think that's the whole point of doing this. This is in the first place. And now if we look at this other metric, so here this is the MSE between the trajectories itself, and in a way the MSE doesn't differentiate the predicted trajectories from a completely random sample at this very long rollout, which makes it like in a way unsuitable for like measuring performance, like generalization performance. And the other one we tried to is this ST here is the synchron divergence, which in a way measures the distance between two distributions. So we induce a distribution of the particles and measure the distribution distance. And again, it's the same. It doesn't manage to like differentiate a random run from what we call a somewhat successful run from the graph neural network. Okay, I think that's all the experience I have. So in summary, we have shown that that graph neural networks manage to like predict emergent behavior in active matter systems, and a few pitfalls we found is that the traditional metrics don't really identify the somewhat better runs than just random, and that rotation symmetry is essential when working with like rigid geometries. Okay, what we're doing now, so that's that. So now the next steps is one thing that we left out of the study is noise, and that's kind of relevant in active matter because this active matter system has a lot of what we call phase transitions, and that very depends on the noise. So what a noisy simulation might look like, something like that. But that obviously complicates how we might train the model in the first place. So so what we did before is like we just predicted the future position, but you can imagine that with noise, rather than having one position here, we have like a whole distribution of possible positions, which suggests that we need to model the distribution. And in machine learning, we call this generative modeling. So what we're trying to do right now is like couple the graph neural network with like a generative model. Right now we're looking at diffusion, but I think that's all for me. Any questions? Yep.
Can you go to the symmetry?
Which one?
That preserves the rotation of symmetry. So you think that you did different from the normal one is that you kept the Xietao Wang-Lin. You don't pass the rotation parameter into the neural network.
Yeah.
This is normal.
So before we also pass, so this relative, this is some, so before we had, so H here, had, so H is the same, so it just has the properties of the particles, but E here had before like the relative positions of the particles. So the moment you pass the relative position of the particles into the neural network, it will break the rotation symmetry. So what we do here is remove that from E and just update them separately here.
And how do you update them separately to a normal equation of motion?
So it's similar to the equation of motion, so it's this equation over here, except of course P here is a neural network, and then psi here is also a neural network. But now we don't have the positions in M, which is this step over here.
How restrictive do you find that temporal downscaling? Because I would imagine that you can't make those steps too big.
Yeah.
Because then the edge that you're like the graph that you put in is so different to the graph that comes out at the end, or at least the relative positions in the graph that comes out at the end. Yeah,
that's true. So there's definitely a limit on how far you can take this. We haven't quite looked into it, but it's not about the difference between the future graph and the current graph. It's more about that's just not possible, because in order to like simulate very far in the future, you need like the intermediate steps as well. So it's like trying to like predict, if you have that language model to predict like 50 words in the future, we are not predicting the middle words.
You know, much into the radius as well that you like? Have you?
Yes. So the radius, well, not depending on the time cycle, but and for the radius, generally a larger radius will give you better performance in terms of like metrics, but will give you, obviously you have more edges to process now. So that will be, so there's a trade-off there. Yeah.
The data that you use for the training are simulated. Like for the Vicsek model, it somehow resembles the blocking where it's try. So did you try to use any real data?
No. So here, everything here is synthetic data. That way we can like control the experiments we do.
A video of just extracted.
Mm.
With behavior.
Well, not particular, nothing. I expect the method to like work. Just this, except I guess real world data could be noisy. Yeah. So you have to deal with that.
What solver did you use for the ground truth?
So I use it's Runga-Kutta order 4th. And then I kept the tolerances quite low because the problem is so stiff. Otherwise, it just doesn't simulate at all.
So is what it's doing, are you training the network to predict the effect of running your forward step 7 times?
Yes. So rather than running 7 times, we run it once.
So you give it the same initial conditions,
Yes.
and then it's able to somehow predict in a lightweight way what the effect of applying your
Right. Yes.
full step like 100 times.
Yeah. So it's the neural network effectively skips several steps. Yep.
What's the advantage of using a graph neural network rather than, or do there exist other methods that you can use?
There are definitely other methods you can use, but somehow graph neural networks have won this space. The reason being that is that the graph neural network it's inherently local. In fact, if you try to put some kind of global attention into it, so in the literature we have like graph transformers and stuff like that, it will completely break down because it will learn some kind of global interaction that there's not. Yeah, completely break down. So you can, so besides graph, there's also been work done in like transformers. Basically anything that can take a sequence should work, except of course transformers are inherently global. So I don't expect them to like do as well. And they're also quadratic. So
In any way related to Anderson acceleration?
Anderson, I haven't heard of it. Can you explain?
It's also an acceleration method in the sense that you can kind of fast forward your solving, so you don't have to do every time step. But it's used in dynamical systems where you've got fixed point.
Okay, here we don't quite have fixed points. The particles are inherently out of equilibrium, so we don't have an equilibrium at all.
I guess you've got something analogous, like there's a stationary distribution of
Yeah, there's in a way non-equilibrium steady state, but the particles are inherently out of equilibrium.
I've read some papers on more fluid related on embedding like physics information into graph neural networks.
Okay.
Is that a direction that you'd consider going in, or are you trying to keep it purely data driven?
Yeah, so for this problem, we just kept it fully data driven, except I guess the symmetry could be in a way fixed in form. But for the noisy part, we're hoping to like incorporate a few of the, in a way, some kind of physics construct in the generative process.
Seems like pretty sharp to be able to bounce things off like right at the surface without like approaching each other on that. Do you have any sense for whether like the sharpness of the repulsion is in any way like could be an issue, right? Like if you have it like infinitely sharp, would you have to have lots more collisions within the training data to be able to work out exactly how behavior is, or like another layer?
So the Gaussian term here we're using is unbounded. So if particles are arbitrarily close, the force is also arbitrarily large. So in the training data, what we did is we just kept the name X, and because the data there's only a few particles in the data, it's like reasonably fast to simulate. But yeah, one thing that we run into trouble is like when you'd have like static particles. So you might have like a trap, and then the particles like are stuck in the middle, and it's very bad for the solver. Does that answer your question?
Yeah, no, yeah, I was just thinking of like ways where it could go wrong, like you're saying, where you could miscalculate the step in some way and it ends up overlapping in some way, and then that situation is not in the training data at all.
No, those like trapping are not.
Yeah, no platform.
Yeah.
I just need to ask about the back propagation. So how it's happening similar with the neural network, or I mean traditional neural network, or it's different, like they're using all the optimizer and minimizing like just function.
Right. So the back. So we minimize the mean square error from the nodes, and then we back propagate through the graph. And then the optimizer we use is a standard first order optimizer. So it's add W.
It's gradient descent.
Sorry?
It's a gradient descent.
Yeah, yes, it's a gradient descent based method. Yeah. Yeah, does that answer your question? Yeah.
Because I don't have experience on this before. The first time I have some. I just need to get an idea.
Yeah, you can it's just standard gradient descent on it, and then back propagate through it. Yeah.
Would you like to thank our speaker again?
Yeah.